So for the work energy lab, you told me that the way I used H is wrong. If it's not H, then is
Well,
it?
it depends on where the friction is acting.
It's acting on the whole string,
The whole thing.
the whole,
Where's the friction's caused? This is kinetic friction.
yeah.
So friction, that kinetic friction is doing work because two things are rubbing against each other.
Yeah.
What two things are rubbing against each other?
The string and the pulley
If it's the string and the pulley,
is on the top.
then H is appropriate.
H
Ish.
is, H as in the height that we found?
Yeah.
Okay.
So,
Sort of. Because it's pulling, so it's not slipping the entire way.
Okay.
is our friction supposed to be negative?
The
Friction? The average friction is it supposed to be negative?
It could be, I mean, whether there's positive or negative depends upon how you define your positive and negative directions. The work done by friction would be negative,
Yeah.
because it's pulling energy out of the system. Well, ideally, not always.
Could you?
Abigail?
If we do a lab tomorrow, when would it be due?
Are we doing a lab tomorrow?
Yes, that's my follow-up.
Probably by the 10th.
But
Okay.
What about on Monday then?
Monday, we have that chapter
Master
eight
set.
master set due.
And then we had the lab too from yesterday.
When's our
will we
test
do a
corrections?
lab on Monday?
All right,
Are we doing a lab on Monday as well?
I haven't gotten that far.
Okay, whatever. Just let us know.
You know, the illusion that I have the entire course planned out before I know who any student is or how fast they can move or
Day
what
by
their
day.
backgrounds are, to me, it's a completely ridiculous assumption.
Valid.
So, I set something up because I have to, and then I ignore it. We'll play it by ear.
I've got my due dates so far. So the lab we did yesterday will be due next Monday.
Yes.
Okay.
okay.
As well as the chapter 8 master set. And then this Thursday is test corrections, chapter 7 master set. And
Yes.
then when's the test corrections for the second
That-
test due? Whenever. Just turn it
Before the end of the 10th.
in. Okay.
If you're
Everything
doing while
is-
I'm still here, you can hand me a paper copy. After that,
Everything is due by the 10th.
yes.
Yes. Yes.
And again, don't send me an email after the 10th asking
not.
what your grade is.
I'm not gonna do that.
If you can't find your grade a week later, yeah, then I'm not quite sure where students see their grades.
Could you possibly, okay, actually I have two separate questions. One is, no, I'll ask you that in your office later.
Okay.
I was gonna ask if something is, are we able to argue a case on a grading?
Yeah, on a one-on-one basis.
Okay. Okay, that's all I wanted to know. And then also, could you possibly like, with made-up data or whatever, just do an example of work through for a pulley friction problem that involves two masses similar to the lab one? I feel like I get it, but I also know what's gonna happen is I'm gonna go home after having talked to you about it today and be like, I forgot everything you said.
Alright.
So I wanna take notes.
With friction.
Yeah, like trying to find,
Alright, I'll start with an extreme case. I have a pulley that will not turn. Mass 1, mass 2. Mass 1 is greater than mass 2. If we do the force diagram here, ooh. Yeah, we'll go from an energy point of view. It's not turning. So this distance here is h. So from an energy point of view, I know that I have do we have that for that? Yeah, we do. All right. So I know that the non-conservative work is equal to the change in energy. Well, the three work energy relationships. So therefore, that's equal to the final energy minus the initial energy. So my final energy is going to be equal to my initial energy plus whatever the non-conservative work that was done. If non-conservative work is negative, then I'm going to lose energy. If it's positive, I'm going to gain energy. An example of positive non-conservative work is if it's going down, mass 1 is dropping, you smack mass 1 down so it goes faster. Friction, classic example of creating negative work in this case. Friction can do positive work in certain cases, it just depends. So, my two types of energy, kinetic and potential. If we set H is equal to 0 down here, then my final potential energy is 0. Actually, I probably should go to the intermediate step. The formula for kinetic energy, 1/2. You all know this. Or should know it. Occasionally I ask my daughter, Anthony, years ago, she sometimes forgets. Matter of fact, she would claim, if you called her up right now and asked her the formula, she would say she doesn't remember. All right, so I filled in some blanks here that obviously formula for kinetic energy, 1/2 mv squared. I don't have anything rotating, so I don't have to bring rotational kinetic energy into it. My potential energy is the one associated with the conservative force involved here, which is the force due to gravity. And even though I haven't drawn it, the pulley is being held up. If I set H is equal to 0 at the bottom, that would be equal to 0 because I said so. My initial velocity, or initial speed, is 0 because I'm going to have it start at rest. So what we have here is our final kinetic energy is equal to our initial potential plus whatever the non-conservative work is. So if it takes a certain amount of time for it to fall, cleverly use the time t. I know that how fast it's going at the end, well, I am assuming constant acceleration. So I have, let's see, final speed is equal to initial speed plus at. Final speed would be equal to g times whatever t is. Therefore, oops, that one. So if my initial kinetic energy is 1/2 times, well, the question is, what is the mass that I should be choosing here? Because I actually have two objects that are moving.
The one that's moving back.
So my equation actually should be, sorry, jumping back here for a second. That's the kinetic energy of both masses, that's the potential energy of both masses. So I probably should take it one step further. I'm gonna drop back for a little bit. So it's K final 1 plus K final 2 plus U final 1 plus U final 2 is equal to K initial 1 plus K initial 2 plus U initial 1 plus U initial 2 plus the non-conservative work. Initially, they both start at rest. So those are 0. I know that my second mass, mass 2, the one hanging out down here, starts at where I set H is equal to 0, so that's equal to 0. And 1 ends up there, so that is equal to 0. So I have 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared plus MGH. Well, it's going to go up at distance h. M2GH is equal to M1GH plus the non-conservative work. I know that the speeds of the two objects are the same. I am assuming that the room is not stretching, that if one object moves a centimeter, the other one will move the centimeter. But they will move the same distance in the same amount of time. Their speeds will be the same. So this is 1/2 mass 1 plus mass 2 times whatever that final speed is squared is equal to M2GH. Try that one again. M1GH minus M2GH plus the non-conservative work. In the lab, you did this. You figured out what that final speed was. This is the final kinetic energy. This is the work that was being done by the force of gravity. So the difference between the two, I would expect this. Let's see if I've done it this way. So initial plus that. Oh, that's right. This is going to be a negative number.
So you were saying in there earlier that the reason why our kinetic energy is a smaller number than our work is because of this, is because at this point we have to now account for friction.
Right. So this is the total work done. This is the change in kinetic energy. And then plus a negative number, because the friction will be doing negative work. So work non-conservative would be the change in kinetic energy minus, in essence, the change in potential energy, or M1 minus M2 GH, however you want to do it. Work is force times displacement. So we're talking friction times displacement. It's going to be equal to the difference between my kinetic energy. It's equal to this. So now comes the question of where is the friction acting? Well, in this particular case, the pulley's not moving, so we have the string that's running over the course of the pulley. So this bit of string right here is going to be moving that distance as that moves the same distance. In essence, the string is going to be dragged the distance h. So this is the friction times h is equal to whatever this is. So friction would be equal to that, which is a negative number. I would expect it to be a negative number, although there's some statistical fluctuations, and it doesn't always work out that way. It's going to be this divided by h.
If the pulley was moving, where would the friction be? Would it be inside?
So now, if it is moving, the question is, where is the rubbing happening?
Is it between the pulley itself and like the bar that's keeping it from going away?
If that's the case, if we look at the pulley, and there's some axle here, if it's the string, then that's basically where the string is touching it. If it's sitting on something, then that's the distance. So as it turns, let's see, this is gonna be, it's gonna be rubbing at the bottom of whatever the axle is, this will be rubbing at the top. Now, in reality, it's gonna be a mix of the two. If we assume ideal static friction between rope and pulley, so the rope is not pulling at all, so the rope is not sliding at all over the pulley, then all the friction is here. So, what's the distance that the friction is acting under?
Is it still the same? It's just H.
I think half of the H. Because it can be the same.
Pardon?
It can't be the same.
It's not the same as in it's not H?
Yeah.
Okay. And as long as we're going and throwing some reality into this, the friction of the rope over the pulley, if there's some sliding going on between the rope and pulley, then that has a different coefficient of friction than the plastic on plastic that would happen at the axis. So when, I guess I spoke to you, I was thinking it's all at the axis, and then later when speaking to you, I was thinking, I guess you could make an argument for it being out on the outer part, but part of it, there's some nebulous information there. I'm asking you to come up with an approach.
Well, you do say on here, what is the average friction on the pulley's axis?
I do say on the axis, okay.
Yeah.
So I'm making the assumption there that the rope is not slipping.
So then I don't understand how it's not, also just H. Because when you were demonstrating, like, when this much rope moves over, is it not still the same thing?
All right, so I've got two things that are rotating here.
Yeah.
If the wheel turns around once, so just one revolution, then I've got that much distance that is covered there. So for one revolution, that's the amount of rope that would have moved.
Okay.
However, here, in one revolution, that's the distance that was covered.
Then how are we supposed to find that?
How would you suggest?
Well, I feel like if we're trying to solve the friction in this equation, and I'm pretty sure based on the way that's based on this problem. I was gonna say based on this problem, if you have friction times H equals change in kinetic energy minus M1 minus M2 GH, and you divide by H, the H's cancel out, so it doesn't matter anyways. Do you see? It might be on the next one.
So H,
It might be on the next page. Nope, it is there. So see how you have FH?
I got H there, and I have H here. I don't have, H is built into my speed there, but it's a speed squared. H is not gonna cancel out.
Never mind. Bummer.
That would be interesting if H disappeared. If H didn't matter, that means that, no matter how far a drop it is, the speed is the same. How very Aristotelian.
Well, then I don't understand how I solve for H in this case. Because it's not like we measured the pulley and know
So that's what you need to know?
I don't know.
I mean, I can pull out a pulley and a caliper and come up with a crude estimate for probably the diameter. If that would help you. Because I think yesterday I said, if there's any information that you might need, just ask.
Yes, but
We didn't know what.
if you could do us all a favor and tell us the right way.
Oh, wait, I think I
Like,
found it.
this has been on the labs before.
Yes. I've given more information here than I usually give, that,
I think I found
Okay.
it. Isn't it,
which doesn't mean that they understood it any better, it means they didn't ask questions about it.
isn't this? Do we have to do that now?
No, that was just the way to find final speed. Alright. Alright, if you wanted a problem with friction, I mean, I can throw numbers in there, but we still, it's simple enough to find the work done by friction. We're still in that pesky part of what was the distance actually traveled. If you know h, if you know the distance that the mass has moved, if there's no slipping between the string and the pulley, you can figure out how many revolutions it took. Because if I have if my circumference here is 0.1 meters, then I know for every revolution that this object has moved 0.1 meters. So if I know this distance, which you should know in the lab, if you know that distance, then you know how you can divide by the circumference, and you know how many revolutions there are.
So we need the circumference of the pulley then.
Okay? You want that?